Section 3. The terminal and the shell. That black window you type into every day looks like one thing, but it's actually two layers stacked together, with an intermediary in between that most people go their whole lives without ever looking into. Here's the full path. Your finger hits a key. The signal goes into the terminal emulator first, passes through something called a PTY, and only then reaches the shell, which then goes and launches whatever program you actually wanted to run. The terminal emulator is just an ordinary desktop application, GNOME terminal. Kitty, all count. Its job is simple: draw text on screen and capture your keystrokes. The shell is the program actually doing the work underneath, reading every character you type, parsing it, expanding it, and deciding what to launch. The PTY in the middle, short for pseudo-terminal, you can guess from the name it's fake, a simulated terminal. That name is a holdover from history. There really used to be physical hardware terminals, teletypes, wired one by one into a mainframe. There's no such hardware anymore, but the software architecture still simulates that old setup, so the shell thinks it's connected to a physical terminal, and old programs written for that era don't need to be rewritten to keep working. Here's a life-saving tip up front. If a full-screen program like Vim or Top crashes, the terminal sometimes gets corrupted along with it. The display turns to garbage, typing doesn't show up. You don't need to close the window, blind type the three letters RESET and hit enter, and the screen usually comes back. I honestly don't know how many times I've used that trick myself. Okay, back to what the shell is actually doing. When you casually type a single command, the shell does a lot more behind the scenes than it looks. Take this one line, lslaw, piped into grep.py, redirect it into a file called files.txt. In that one short line, the shell does at least four things. It splits the whole line into individual tokens. It spawns two separate processes, one running ls and one running grep. It connects the standard out of the first process to the standard in of the second. And finally, it redirects the whole result into the file. Here's a key thing to remember. ls and grep have no idea a pipe even exists. The shell wires that connection out before it ever launches them. The two programs just obliviously read their own input and write their own output. In other words, a program only cares about reading standard in and writing standard out. Who connects to whom and how is the shell's business. It has nothing to do with the program itself. That's the concrete implementation of the Unix philosophy. Each program does one thing well, and something else handles composing them together. The handout's about to warn you that the shell is a minefield. Here's a rule you really need to memorize, because when you start writing shell scripts, this is exactly where things go wrong. Inside double quotes, a $sign variable gets expanded. Inside single quotes, nothing gets expanded. What you see is exactly what you get. As far as the shell is concerned, these two kinds of quotes are completely different things. That rule happens to explain something else too. Why experienced people never put spaces in file names. The shell splits into tokens on whitespace. So if a file name has a space in it, that one file name gets sliced into two separate arguments, and the program receives something that's not the file name you thought it was. Which is why experienced engineers stick to lowercase letters, digits, hyphens, and underscores in file names. Looks plain, but it guarantees you'll never step on this landmine. Now back to the landmine the handout actually warns about. Say you write a cleanup script with a line like rmrf, followed by a double-quoted $sign directory slash. Looks fine at a glance, right? The problem is, if that directory variable is never set, inside double quotes it just expands to an empty string, and the whole command instantly turns into rmrf/ment to wipe a subdirectory, and instead it wipes the entire root file system. That's not an exaggeration. It's purely the natural result of double quote expansion combined with an unset variable, two things that just happen to line up. So experienced people build three nearly obsessive habits. Always double quote variables. Before you actually delete anything, echo the expanded result first and look at it with your own eyes. And once a script is done, run it through shell check before it ever goes live. Shell check is a tool you don't even need to install. There's a web version, shellcheck.net, paste your script in and it flags exactly this kind of landmine. It's so convenient I genuinely can't think of a reason not to use it. Bash, by the way, is the shell built by the GNU project, and it's the default on most distros. There's a distinction a lot of people mix up, and it actually matters a lot, that one config file called ~/.bashrc doesn't get read every single time you open a shell. An interactive shell, the kind you open as a terminal window and type into, reads ~/.bashrc, but a non-interactive shell, the kind you get running bashscript.sh, does not read it. A login shell, the kind you get logging in over SSH, reads a different file entirely, ~/.profile. That also explains a classic symptom. A command works fine when you type it in the terminal, but when you put it in a script it says command not found. 9 times out of 10, the setting you need is written in a file that never gets read in that context. I'll do a full dissection of this in the path section. For now, just keep the impression in mind. You just need to know the other shells by name, not master every one of them. Z shell is now the default on macOS. The interactive experience really is a bit nicer than Bash, with prettier completion and themes, but people still tend to write scripts in Bash, since compatibility is the safest bet. Fish is great out of the box. But its syntax isn't POSIX compliant, so it doesn't play well when sharing scripts with others. Dash is small and fast on ubuntu/bin/sh actually points to dash, not bash. So here's a practical rule to check whenever you write a script. If you're using a bash-only feature, spell it out explicitly in the shebang line as /usr/bin/nvbash. If the shebang says /bin/sh, then you're stuck with strictly POSIX compatible syntax. Use a bash-only feature there, and it might just blow up on a different machine. Section 4, the file system. Unix has a defining design principle you can sum up in one line: everything is a file, everything gets treated as a file. Hardware devices like your keyboard and mouse are files /dev, the live state of running processes is files /proc, the current state of the kernel and hardware is also files /sys. That's not just a slogan, it's genuinely usable. Run cat/proc/CPU info and your CPU model and core count print straight to the screen, because the kernel wrote that information out as something you can read the same way you'd read a file. Why design it this way? The benefit is you don't need to learn a whole separate API just to read hardware info, process state, or network configuration. As long as you know open, read, and write, the most basic operations, you can in theory interact with almost anything in the system. Learning to read and write files is basically learning the key to observing the entire machine. Second rule, and you need to drop your Windows mental model here, this is a tree. There's no C drive, no D drive. There's exactly one root, a single // and every other disk, partition, USB drive, or even network file system is a branch grafted onto that same tree. That grafting operation is called mounting. Mounting takes the directory you mount onto and temporarily covers up whatever was already in it. Once you unmount, the original contents reappear. So if you ever find a directory acting haunted, where a file should clearly be there but you just can't find it, don't assume the file vanished. Run find_mount to check exactly which file system you're actually standing on right now. Very often something got mounted in the wrong place. Mount, dfh, and lsblock are the three basic commands for this. I'd suggest opening a terminal right now and trying them yourself. For everyone coming over from Windows, here are 3 things the handout doesn't mention, but that nearly everyone genuinely runs into. First, case sensitivity. Makefile and makefile are 2 completely different files as far as Linux is concerned. Windows by default can't tell the 2 apart, and when a Git repo syncs between the 2 machines, this is exactly where bizarre errors tend to show up. Second, the file extension is purely a convention for humans. The system itself never relies on it to determine a file's type. If you get a file you don't recognize, instead of guessing from the extension, just run the file command and ask it directly. It reads the first few bytes of the file, the so-called magic bytes, and tells you exactly what it actually is. Third, and probably the most painful one, there's no recycle bin here. RM deletes something and it's really gone, no undo button to press, so anything that actually matters needs to either go into Git version control or get backed up separately. Skip both, and you've effectively opted in to losing that data, nobody to blame but yourself if it happens. Directory conventions worth memorizing until they're reflexive. /bin and /usr/bin hold programs, /etc holds system configuration, /home is where your account lives. While root's home is kept separately at /root, /var holds data that keeps changing, with logs collected under /var/log/temp is scratch space, usually wiped on reboot. If you carelessly dunk your experiment's result files in /temp, you're basically signing up to learn that lesson the hard way. /opt is where large third-party software lives. CUDA, ROS, that kind of thing usually gets installed there. /proc and /sys are the 2 virtual file systems I mentioned earlier. 4 reflexes worth keeping in mind: look in /etc for configuration, /var/log for logs, home directory.files for personal settings, and suspect /var first when the disk fills up. Speaking of a full disk, here's the whole investigation workflow. You'll need it sooner or later on a shared machine. Start with dfhh. To see which file system is full, then /+ a path, working your way down layer by layer to find who's actually eating the space. If going layer by layer feels like too much work, just run sudo apt install ncdu. Once it's installed, opening it gives you an interactive leaderboard showing exactly who's taking up the most space. Basic operations. I really want you to actually type these yourself, not just watch pwd, lslaw, cd, make directory p, cp, mv, rm to find files by name, use find with name and a pattern like star.py. To find content inside files, use grep or rg instead. Keep the division of labor clear. One searches names, the other searches contents. Paths come in 2 flavors, absolute, starting from that single root /, and relative to whatever your current working directory happens to be. 1 dot means here, 2 dots means 1 level up, and tilde means home. Here's a landmine people commonly hit. Be careful of this when writing scripts. A relative path is relative to the current working directory of the process at that moment, not to wherever the script file itself happens to live. A lot of people mix those two up, and the script breaks completely when run from a different location. Before you actually run rmrf, build the habit of pausing for a beat. If you're not sure, add a AV flag to see exactly what it deletes. An even safer approach, run ls first with that exact same path string, look at the list with your own eyes, confirm it's what you expect, and only then swap ls for rm. That habit costs less than 10 seconds and can save you a lot. Every file carries metadata, that long string at the start of lsl output, something like rw-r-r-. The first character is the type, a dash for a regular file, d for a directory, l for a symlink, then 3 groups of rwx corresponding in order to the owner, the group, and others. To see the full metadata, run stat. There's a detail a lot of people miss but genuinely get bitten by. For a directory, the xbit means whether you can pass through it. Plainly put, whether you can use that directory as a waypoint in a path. If any directory along a path is missing its xbit, it doesn't matter if the file itself shows R, you still can't read it. I've been burned by that one myself. Let me wrap up with 3 small things. First, symlinks and hardlinks are not the same thing. LNS target link name creates a symlink, which is essentially a shortcut pointing to a path. Move or rename the target, and the shortcut breaks. Skip the S and you get a hardlink instead, which points to the same underlying data itself. Normally you can't tell the difference, but it shows up when you swap versions or replace the target file entirely. Readlink lets you check exactly where a symlink actually points. Second, dot files. Any file name starting with a dot is hidden by default. You need LSA to see them. Put your own dot files into a Git repo, and when you get a new machine, a single Git clone brings your whole familiar setup right back. This is one of the best return on investment habits early in grad school. I only learned this the hard way myself after reinstalling machines a few too many times. Third, file system types. ext4 is the common one locally. Plug in a USB drive and it's usually exFAT or FAT32. FAT32 has no permission mechanism and no concept of symlinks. That's not a bug, it's just that those fields were never designed into the spec back in the DOS era. Cross-system compatibility is its strength. Permission control was simply never the problem it was built to solve. Section 5, Users, Groups, and Permissions. This model dates back to the 1970s. Imagine an extremely expensive mainframe shared by dozens of people. The system needs some way to know exactly who's typing this command and what that person is allowed to touch. Every user maps to a UID, every group maps to a GID. The names are for humans, the kernel, deep down, only ever knows numbers. When you run whoami and see an account name, the system is really just looking that number up in /etc/password and translating it into a name for you. UID 0 is root. I think the handout's definition here is precise and worth writing down. Root is the user for whom permission checks simply don't apply. In other words, every gate that stops a regular account doesn't exist for root. Getting root means getting total control of the machine, so the correct posture is to keep your distance. Borrow it briefly when you need it and hand it right back when you're done rather than staying logged in as root the whole time. To check your own identity, run whoami, ID, and groups. Run all 3 and it's clear. Groups are a wholesale mechanism for permissions. Grant a permission to a group first, then add whoever needs it into that group. One grant, many beneficiaries. For example, sudo usermod ag dialout user. Serial devices like /dev/ttyusb0 are often assigned to the dialout group. Anyone working with robotics hardware or dev boards will run into this sooner or later. Wanting to run Docker without sudo works the same way. Just add yourself to the Docker group. 3 landmines here to watch for. That A in AG stands for append, meaning add on top of. Forget that A, and every other supplementary group you already belong to gets wiped and overwritten, leaving only the one group you just specified. Group changes don't take effect immediately. You need to log back into the system for it to show up. And one more thing to keep in mind. Adding yourself to the Docker group is, practically speaking, equivalent to getting root without a password, because Docker's own permissions are high enough to touch the entire machine. That's not an exaggeration. That's literally how it's designed to work. Now let's decode RWX. Here's something commonly misunderstood. Permission checks only look at the one group that matches. They don't add all 3 groups together. The system first checks whether you're the owner. If so, it uses the first RWX group's result and stops there. It won't keep checking further down. If you're not the owner but you belong to the files group, it uses the second group. If neither applies, only then does it fall to the third group, others. The groups are mutually exclusive, not additive. The logic behind the numeric notation is R is 4, W is 2, X is 1, and adding the 3 numbers together gives that group's permission. 755 is RWX, R-X, R-X, common for executables and directories. 644 is RW-, R-, the default for a regular file. 777. The handout literally draws a forbidden symbol next to. It means any program on this machine, run by anyone at all, can freely rewrite this file. Which is basically ripping the door off entirely. Nothing stops anyone from walking right in. Let me add a real-world use of 600 the handout doesn't cover, but that you'll very likely run into this week, SSH keys. If the private key file under ~/.ssh has permissions that are too open, the SSH program will flat out refuse to use it and print an error saying permissions are too open. Almost everyone hits this the first time they copy an old key from one machine to a new one. The fix is simple. chmod 600 on the private key file. This is actually one of the few places the system forces you to actually understand permissions, and it also explains what 600 means. Only the owner can read and write, and nobody else can even open it to look, which is exactly the level of protection a private key deserves. Another one you'll use constantly is chmod +x. A script you download straight from the internet has no execute permission by default. You need chmod +x first, and only then can you run it as /script.sh. Git, on the other hand, records the execute bit directly as part of the file when you commit it into version control. So the same script, when cloned from a Git repo, usually already carries that execute bit and can be run right away, no manual chmod needed. Same exact file content, but downloading it from the web versus Git cloning it behaves differently. And that difference is hiding in the execute bit. That's also why sharing a tool script you wrote is better done through a Git repo rather than passing around a zip file. 3 special permission bits you should be able to recognize on site. The set UIDs bit. This is exactly what the password program relies on, letting a regular user temporarily borrow root's identity to write to /etc/shadow, the password file only root can normally touch. A lot of privilege escalation bugs trace back to a carelessly set UID program. The T at the end of /temps permissions is the sticky bit. Everyone can write into that directory, but only the owner of a file can delete their own file, which stops someone else from accidentally, or maliciously, wiping your temp files. setgid is commonly used on shared project directories, set-it, and any new file created inside that directory automatically inherits the directory's own group, saving you from manually fixing the group every time. Last one, sudo, is, at its core, a form of logged borrowing. Compare that to su, which fully transforms you into root and keeps you there for everything you do. Sudo borrows it once per command and hands it right back afterward, and every command is logged for review. The /etc/sudoers file can even break down exactly who's allowed to run which commands. Authorization can get very granular. 2 practical details the handout doesn't mention. First, to edit the sudoers file, always use the dedicated vi-sudo tool. It checks the syntax before it lets you save. If you go edit it with a regular text editor and your finger slips on a single character, breaking the syntax, you can end up in a situation where nobody on the whole machine can sudo anymore. You've locked yourself out and even root can't get back in. That kind of situation usually needs a rescue mode to fix, and it's a real hassle. Second, a lazy little trick. You type out a long command, hit enter, and only then realize you forgot sudo. No need to retype the whole thing, just type sudo, space, bang bang, and bash will take your previous command and rerun it right after sudo, verbatim. On taste, the handout puts it well. Seeing permission denied and reflexively slapping sudo in front of it is the habit you most need to break. If you need sudo just to write a file inside your own home directory, that means something is actually broken, and the thing to fix is whatever's broken, not reach for sudo every time to force your way through. As for why sudo pip install is basically forbidden, I'll leave that for the next section to unpack properly.